Okay, our next speaker has been given shout outs in many of our talks earlier today. We have Dr. Renee Weber talking about the Artemis 3 Science Definition Team. Take it away, Renee.
Hi, Kelsey. Can you hear me okay?
Loud and clear.
Great, thank you. So I just wanted to start off by saying not only thank you for the invitation to come and present again on the Science Definition Team report, but also thank you to the actual Science Definition Team. If I could get the first chart, please. So all of these folks from across the agency and from the broader community participated in this really breakneck activity. It's only been 4 months, a little over 4 months since we submitted the final report to headquarters, but a lot has happened since then. In the first part of my presentation today, I apologize if you saw my presentation in the last Lunar Surface Science workshop. It's going to be a little bit similar to that, just walking you through the process of putting the report together. And then in the second half, I try to tailor the section of the presentation where I talk about the recommendations made in the report. I try to tailor that to each audience. And so if you've seen my previous surface science workshop presentation or any of the other venues where I've presented these, you're probably closing in on seeing the complete roadshow. So again, I apologize for that repetition. Next chart. Okay, so the Artemis 3 Science Definition Team was chartered by SMD, by Thomas Zurbuchen, in order to define compelling and executable science investigations for the Artemis 3 mission. This will be, of course, the first human mission to the surface of the moon in the 21st century. And our report is available publicly. You can get it at nasa.gov/reports. So if you haven't had a chance to look at that report in depth, I encourage you to go check it out. Next chart. So what the Science Definition Team was really tasked with doing was expanding upon the 7 high-level science objectives that were laid out in the Artemis plan. Those are understanding planetary processes, understanding the character and origin of lunar volatiles, interpreting the impact history of the Earth-Moon system, revealing the record of the ancient sun and our broader astronomical environment, observing the universe and the local space environment from a unique location, so essentially using the moon as a platform, conducting experimental science in the lunar environment, and investigating and mitigating exploration risks. So the Science Definition Team was charged with expanding upon these objectives, and we did that through a traceability exercise where we mapped science goals, which are specific areas of research, down to science investigations, which are specific activities undertaken to address those goals. Next chart. And since we are, of course, not the first group of people to think about doing science on the lunar surface, we largely identified our goals and investigations based on recommendations that were made in existing reports and sources, as well as drawing from the 126 community-submitted white papers that we solicited specifically for this activity, and feedback that we got during a draft writing phase of the report. So I know many of the folks that submitted white papers are probably on this call today. I just wanted to thank you for that effort. We continue to refer to these white papers, and they are also all available online. So really quickly, I'll just run through our guiding documents. They are the League Lunar Exploration Roadmap from 2016. As well as the 2007 SCAM report, the scientific context for the exploration of the moon, and its 2018 assessment, also by League, the Advancing Science of the Moon report from the Lunar Explorations one of the special action teams that League chartered, and then finally the current planetary decadal survey. Next chart, please. So through this activity, the Science Definition Team constructed a notional program that captures the highest priority science for Artemis 3, as well as provides the greatest feed forward to follow-on missions and to the build-up to the Artemis base camp. And so several of the other presenters today have referred to this program already. It contains a mix of cohesive activities that include sample collection and return, in situ and field science, and deployed experiments. And this candidate set of activities taken collectively would address the highest investigation priorities identified by the SDT, as well as a multitude of additional investigations. And so the idea was that this report, the traceability exercise that we did in this report, is intended to be built upon for subsequent Artemis missions. But I will mention specifically for Artemis 3, a more detailed mission operations plan to actually carry out this candidate program needs to be developed when certain pieces of the architecture come into sharper focus, like the HLS system capabilities and the landing site. Next chart, please. So the first part of the program is samples. Sample return for Earth, of course, addresses a wide range of investigations, not just those that were highly ranked. So this table here maps out the types of samples and the number of samples for both the threshold and the goal mass, up mass capability, or requirement, I should say. And then these numbered investigations refer to specific investigations in the traceability matrix in the report. So I encourage everyone to go and cross-reference this table against those investigations if you want to dive into more detail. So the committee recommended both traditional sample collection, like rake samples, as well as advanced techniques like both hermetically sealed and cryogenically maintained regolith core samples to preserve volatiles that may be present in the soil, which is, of course, important since we are going to the South Pole, partially because of that presence of volatiles. And then lastly, maximizing science from returned samples does require continued investment in terrestrial curation facilities, which includes cold curation. I'll talk a little bit more about that in a minute, as well as laboratories, analysis techniques, and workforce to make the best use of the returned samples. Next chart. So the next two legs of the program are both in situ and deployed science. The HLS down mass allocation, at least the requirement for science and utilization, of course, must first be reserved for the tools and return containers required for sample collection. And therefore, whatever mass is left over may be limited, but that will be the allocation available for both in situ tools like handheld instruments, as well as crew deployed instruments that may be left behind on the surface. And so the SCT pointed out that to envision or to maximally enable this list of measurement techniques shown here in this table, we would be wise to think, it would be wise to think about measurement techniques that address multiple investigations, as well as have the ancillary benefit of increasing crew safety or reducing risk for future missions. And so, those techniques include volatile monitoring in situ, deployed environmental monitoring, deployed geophysical monitoring, in situ geochemistry and mineralogy, in situ geotechnical properties, and then also in situ geophysics. So that would be something like traverse instrumentation. Next chart. Okay, so the SDT report itself contains 15 major findings and accompanying recommendations for NASA to, actions to help NASA address each of the findings. Those encompass crew training, sampling strategies, enabling capabilities, which includes technology development, Artemis program architecture, science implementation strategy, cartographic considerations, as well as landing site selection criteria. And so the three that are highlighted in blue are the three that I'm going to focus on today because, in the spirit of providing an update on where we are with the recommendations made by the SDT report, these are the three where I have sort of the most information to convey. Next chart, please. So the first is enabling capabilities. The report recommended that NASA develop lightweight, double-sealed vacuum containers to return volatile-bearing lunar samples to Earth. And then furthermore, the report also recommended that NASA develop and implement hardware and operations for cryogenic sample return. So temperatures that are low enough to preserve water, ice, and other volatiles of interest in the solid state throughout the journey from the moon to Earth, all the way back to Earth-based laboratories. So of course, cryogenic sample return really increases the scientific fidelity of sample analyses of both volatiles and ices. And then, of course, in both cases, we want to minimize the mass penalty because of that potentially limited down mass capability that I mentioned earlier. So we want to maximize the amount of actual sample return instead of the mass of the sampling hardware. So in this area, we do actually have a multi-program study underway right now looking at the cold stowage chain, both active and passive systems. Teams looking at both vehicle capabilities and science requirements and seeking joint solutions, obviously, as well as performing technology searches in parallel to the activity to inform the study. So we're looking at several different options here, taking the report recommendations into account. Next chart. Some other enabling capabilities. So one of the recommendations in the report focused on what we called sort of opportunity lost. If the first of a series of both geophysical and environmental network nodes is not deployed, so this would be similar to something like what was done with ALSEP during Apollo. And then the Artemis 3 node can be augmented by both future robotic and human missions, and that would build towards a global network of observations. And so while we might be able to do incremental science with individual short-lived experiments, the report recommended that NASA continue to pursue options for both long-lived power and communications, which are both requirements needed for an ALSEP-like package. So that's going to allow meaningful progress on many of the science goals and, of course, provide feed forward to future missions. And then lastly, there was a specific recommendation in the report for geodetic monitoring via Earth-based laser ranging. So, once positioned, a laser retroreflector requires no power and no communication. So it provides science return even in the absence of those capabilities. So the report did advocate for that capability on Artemis 3. Next chart. And so following on the recommendation for communication capability, which is of course important for instruments deployed on the surface, it also enables sort of real-time communication, two-way transmission of data, as well as contact with the science support team on the ground, which will be useful for EVA ops. So that's essentially real-time feedback to the crew on science decision-making and helping provide process data when necessary. So this is going to require the establishment of high bandwidth communication capable of extensive real-time data transmission. So there's a recommendation in the report on that. Next chart. So the next category of recommendations focuses on the Artemis program architecture itself. Looking at things like I already mentioned, soliciting the development of instruments that are capable of addressing more than one measurement need and or more than one science investigation. Also potentially looking at the pre-positioning of assets in the vicinity of the Artemis 3 landing site. So there are studies looking at whether or not this is feasible as well. Pre-deployed assets could consist either of some kind of inert cache of tools or instruments that are accessed by crew after they arrive on the surface, but could also be something like an instrumented lander or even a rover to perform environmental monitoring or to be operated telerobotically. And then there was actually a separate mobility recommendation for mobility solution for crew to use on the surface as early in the Artemis program as possible. Vehicle downmass capability is going to be directly relevant to many of these issues. And of course, when the HLS selection is finalized, we'll be working very closely with our partner to ensure that science and utilization needs are met in this area. And next chart, which I think is my last chart, final recommendation on science implementation strategies. So there's been a lot of work done here. So the report recommended a standing working group, a working group be stood up to comprise science leadership of the Artemis program within SMD and HUMD. And you've already heard from the people who run those groups. So we've been working very closely with Julie on the utilization coordination group. There's also a group in AES. So lots of groups stood up to ensure that science is at the forefront of Artemis decision making. And then, of course, we continue to rely on our program analysis groups like LEAG and like XMAG, which serve a very important role synthesizing input from the broader community. So we want to make sure that we give as many opportunities as possible for community participation. So that's the end of my presentation, and I'll hang around until the questions time if anybody has any specific questions for me. Thanks.
Thanks, Renee.